All right. Um, so one of the question is to repeat the definition of node and antinode. I might explain it the way that confuse you more than it should. Antinode is just the location where you have the constructive interference. Okay. Node is where you have destructive interference. Okay. So if at that particular position you found out that the wave add up constructively, then we call that point to be antinode. Okay, so antinode or node is just the the name that you attach to that particular location, whether the wave you get is gonna be constructive interference or destructive interference. Okay, so in terms of sound wave, like in this case, um, constructive interference, you're gonna get you know sound wave which is louder when you hear it using your ears or detector. So antinode is everywhere which you have like loud sound, and node is where you have almost 100% quiet sound or very soft sound because you have destructive interference. Okay, so to summarize, like antinode, it just means that particular point is a constructive interference point, and node is just the destructive interference. Okay. Um, next thing we're going to talk about standing wave, and the notion of node and antinode will comes up again. So let's see if that makes more sense or not. Okay, but is this clear to you in terms of what we have talked about so far? Well, if not, then you can maybe ask again after we talk about standing wave. We should clear um, something up. All right, so let's talk about standing wave. Um, standing wave is just another form of interference, except the two waves that interfere each other is not really coming from two different wave sources. Like what we have up here is we have two speakers, right? So the wave interfering is the wave coming from the top speaker and the one from the bottom speaker, right? Standing wave is a little bit different. We have to kind of step back a little bit and talk about what happened when wave reaches the end. So when you have, let's say, well, let's not talk about sound wave for a moment. Let's talk about wave on the string. And usually the string is not infinitely long, right? You have to end the string somewhere. So sometimes you end it by attaching it to the wall like this. Okay, so you just fix it to the wall. And this is what we call the fixed end. And then when you send in some wave, right, because when wave hits the end, it cannot go any further because that's the wall, right? I mean, it cannot go into the wall. It has to reflect back. So when you send the wave from the left and the wave traveling to the right, when it hits the wall, it will reflect back. So there will be some reflection coming back from the end of the rope. Well, the rope or the string is a medium. So if you have the end of the medium, then it will have some reflection back. Okay, so reflection means the wave is going to come back like this, right? So if you keep sending wave to the right, and wave going to reflect back, so now you see where the two waves come from. Okay, so standing wave essentially is the interference of the what we call incident wave. I misspelled incident wave, which is what you send in, and reflected wave, which is what's coming back like this. Okay, so interference of the incident wave and the reflected wave. So two waves interfere each other, right? It doesn't have to be coming from two, distinct sources. In this case, it's from the same source, but one is going to the right, one is reflected back like this. And we just need to find out what's going to happen. But in terms of standing wave, it's really what it is, only this one. Okay, nothing too complicated. All right, so let's maybe try to, write down the mathematical calculation here to maybe see how it works. Remember, wave obeys superposition principle. So what we need to do, we just need to write the two waves together and add them. So the incident wave is the wave traveling to the right. So I can say it's amplitude A sine kx minus omega t. Okay. So this is wave going to the right. So I just put an arrow like this going to the right. So that's what we call the incident wave. Incident wave. And then the reflected wave has the same amplitude. But the only thing difference is the direction of the propagation is going to the left. It's traveling to the left. How do we do that? We have to flip the sign here from negative to positive. Okay, so it's the same thing as shifting the graph to the right, you subtract something. Shifting the graph to the left, you have to add something. So this is exactly the same here, right? So the sign between kx and omega t, that's what determines which way the wave is traveling. So in this case, the wave is reflected, so it's traveling to the left. So we have a different sign here. Okay, and because of the sign difference, it makes everything a lot more complicated than what we had before, because you cannot just add them, you cannot just subtract them, because the argument in the sign function, they are not the same anymore. So what can we do? Well, we can use what we call the trigonometric identity, and some of you might remember. If not, then it's fine. I'm gonna remind you now. So if you have sine of A, whatever A is, and you add another sine of B, whatever B is, then it can be shown, although it's quite not trivial to show this, right? It's a very interesting exercise for you, so some of you might be interested in this, to try to prove this. But anyway, the resulting is you can get sine of A plus B over 2, okay, the whole thing inside the first sine function, and then the second one is cosine of A minus B divided by 2. Okay, so this is what we call like I think the sum formula for sine or something, right? But if you don't remember, you can either just look up in the trigonometric identity table. But again, if you have time, you can try to prove this. All right, and that's exactly what we have here. Because A is exactly the first term here, which is kx minus omega t. And B is kx plus omega t, right? So that's exactly what we have here. So we can apply this formula to figure out what is the result. So we're gonna have y of x and t equal to 2, right? And then a is a common factor, so I can just take it out. It's not gonna be anything to do with a in the formula. And then the number 2 is from the formula. And now it's the sign of the average, right? So a plus b over 2. So you have kx minus omega t, that's a, plus kx plus omega t, that's b, and the whole thing divided by 2, like this. So that's the first term. The second term, you have the difference. So kx minus omega t minus kx. And because of the minus here, we have to put the minus sign, right? Again, it's a minus the whole thing. So don't get confused here. And then the whole thing divided by 2. And we can do some cancellation, right? Because kx survive, omega t cancel out. Kx did not survive, but omega t survive like this. And the minus sign inside cosine is fine because cosine of x is equal to cosine of minus x. And the factor of the 2 in the denominator cancel out what you have in the numerator. So in the end, what you have is y of x and t equal to 2a sine kx. Right, so if you're confused, check the math yourself to see that this is what you get indeed in the end. All right? So this is what you get adding the two waves together. And it's a really strange kind of looking function because it doesn't look anything like what we had seen so far. This is what we call standing wave. And it's called standing wave because just looking at this function, you cannot tell whether it's going to the right or going to the left. Because remember, if we want to say if the wave is going to the right or left, you need to look at the relative sign between this kx and omega t. Right? If it's negative, then it's going to the right. If it's positive, then it's going to the left. But there's no such thing here. So that's why standing wave is because the wave itself does not really go to the right or go to the left. It's just standing there. Okay, that's why it's called standing wave. And to see how it looks like as a function of time, it's gonna take a little bit of imagination. So it's gonna do the hard way first, and then I'm gonna show the animation to reinforce your understanding. Hopefully that works. All right. So just bear with me for a few minutes for this. So how do we plot this? Well, let's just pick any time, or not just any time. Let's just pick time equal to 0. So just one snapshot of time. So at t equal to 0, cosine of 0 is 1. So y is just 2a sine kx. Okay. So at t equal to 0, the graph looks like a regular sine function like this. Okay. But then what happened when t equal to something else? Let's say t equal to half, not half, a quarter of the cycle. Actually, I should write it like this. So I choose t to be pi over 4 omega. It looks really strange, but the reason why I'm doing this is because if t equal to this exactly, then cosine of omega t is just cosine of pi over 4. Okay, so hopefully this, I want to use the blue color to indicate the time. So t equal to pi over 4 omega. Okay, t equal to pi over 4 omega. Let me rewrite omega in terms of the period. If you remember what is omega, omega is, I write it here, 2 pi f, which is 2 pi over the period. Okay, just using the definition that we had before. So that means this is pi over 4 omega, which is 2 pi over the period, so t here. So it's just, 1/8 of the period. Essentially, that's what I'm doing here. All right. And 1/8 of the period, okay, t over 8. So it's cosine of pi over 4. So that means y is 2a sine, I'm running out of space here. Actually, I'm not using the space efficiently, so I'm gonna write it here, right? But here is the cosine of omega t, but omega t is pi over 4, right? So what is cosine of pi over 4? That's just 1 over square root of 2, right? So you have like 2 over square root of 2a sine kx, which is just the same graph, but the amplitude is a little bit lower, right? Because 2 is 2. 2 over root 2 is root 2, so it's 1.4 roughly. So it's a little bit less than 2. So, but the graph still looks like sine curve, except the amplitude gets lower. So if we want to be consistent with the upper diagram, I should draw something like, I shouldn't draw it like this. I should draw the same sine curve, but with less amplitude, like this. Okay, so that's when time is the period over 8. Now let's step a little bit forward. Let's say time is now t equal to pi over 2 omega. And that's going to mean time is just a quarter of the period. Okay, so what is this? This is when y equal to 2a sine kx. Now cosine of omega t now is pi over 2. Okay, cosine of pi over 2 is 0. So you're multiplying 0 here. So at this moment in time, the wave is actually a flat line because y is 0 everywhere. So to draw this one, well, it's very easy. By the way, the lambda should be the same. I draw it very badly, so I have to forgive me for that. But it's going to be a flat line like this. Okay, and then another time I'm going to skip the math now. So it's going to be next step, which is 3 over 4 omega. So now it's going to be 3t over 8. Okay, and in this case, you're going to have y equal to minus 2 over root 2 a sine kx. Okay, so you can check the math yourself, but what you get is you get the flip sine function like this, and then at the last step, at least for now, is pi over omega, so that's just half the period, and that's when you have y equal to minus 2a sine kx. So it's become something like this. Okay. All right, so I'm not sure if you are more confused, less confused, but when you see the animation, I'm gonna show you in a few moments, this should all make sense. Okay, but this is the time evolution of the standing wave. So you can see what's happening here. The wave itself does not really travel to the right or to the left, just like what we said earlier. It's the same sine wave, but it's just the amplitude getting shrink or getting larger again as time progresses. Okay, so this is how it looks like. And when you run the time further, it's gonna keep repeating this. And this is what it's gonna look like. So I'm gonna show you this animation here. And look at the blue one. Actually, the one I want you to look at is probably this one. So let's just look at that one. Okay, the third one. That's how the standing wave evolved in time. Okay, and that's what I'm trying to plot earlier. Right. So it's just a sine wave going up and down. There's no movement of the wave It's not going to the right or it's not going to the left. Okay, so that's what we have for standing wave. The problem why I'm emphasizing a lot on this is I'm trying to tell you how it looks like when time increases, when you have the progress in time. It looks like what you have down here. But in the textbook, no matter what textbook you choose to read, because in the textbook it's printed on paper, it's very hard to demonstrate this animation in a still picture. In the book, always you're gonna see the picture which is drawn like this, and it's very confusing if you don't know how it should look like. Okay, so for example, like here, this particular pair of diagram, this is what it should look like. That's the standing wave, okay, which is going up and down like this as time progresses, right? But in the book, usually it's drawn like this. But you have to understand that what it's trying to show is the animation down here, okay? Actually, that's all I want to say here. All right, and you're gonna see in a few moments that standing wave can have different wavelength and different frequency, right? All you have down here, they are all called standing wave, but they are standing wave at different frequency. And later on, we're gonna learn the term harmonics. So it's just standing wave of different harmonics, right? But again, because in the book, it's very hard to convey this animation. So in the book, it's always written like this, like statically, like this. And it's very confusing. But I don't know what's the better way to draw it in the book, right? So that's why the animation helps a lot in this case. All right, so hopefully you understand now that this is how it should look like. Okay? Before I go any further, is there any question? Because I want to make sure that this is clear to everyone what I'm talking about here. No question. Everything is clear. That's great. All right. We're gonna come back to this. Next, I want to show you another animation, which is this one. All right. This is everything I have said in the better kind of animation. So I'm gonna start because it's kind of slow. All right. So what we have here is wave coming out from the left, traveling to the right. It's gonna hit the wall soon. Okay. So the red one is the what we call incident wave. All right, so let's wait a little bit until it hits the wall. So it's gonna reach the end now. Okay, so I'm gonna pause for a moment here. There's a lot going on at this moment. The red one is the wave going to the right, that's the incident wave. Because you cannot go any further, the wave has to reflect back, and that's the blue wave. Okay, so the blue wave is the wave traveling to the left. You can see that it's doing that. Okay, and the red one and the blue one interfere each other and give the standing wave, which is the black dots. Okay, and right now all the region is covered by both waves. So now you have standing wave throughout the region. The black one is a standing wave. Okay, you can see that it's just going up and down. This is how the standing wave should look like. Okay, so I'm not going to say anymore like how you would depict this in the paper or in the textbook. This is how in your brain it should look like. So your brain should be playing this animation when you look at standing wave. Okay. Now you see some letters, which is A and N, right? And this should remind you of something that we talked about before the break. That's the antinode and node that we talked about, okay? So does it make sense? Well, remember what the antinodes are. The antinodes are when the interference of wave is maximum. It's constructive interference. And you can see that the standing wave has maximum amplitude whenever you have the letter A, right? So that's why we call the antinode. On the other hand, the letter N tells you the node, and the node is always when you have destructive interference. Okay, so no matter what time you pick, the letter N gonna give you 0 amplitude, no matter what time it is. Okay, for the antinode, there might be one instant of time where the wave is 0, but that's just one instant of time. For example, like here, right? This is kind of like 0 everywhere. It doesn't mean that the antinode becomes node, because if you talk about antinode, you have to look at any time, right? You cannot just pause it and then say, okay, look, there's no wave here. It doesn't work like that, because you have to just run it. And then, wave has to move, right? So the antinode is where the oscillation is maximum, but the node is always going to be the point where you have no amplitude, like this, okay? So A and N here is the node and antinode that we had earlier, okay? So now I'm gonna talk to you about the condition of standing wave, because if we go back here to this animation, right, I told you that everything that is shown here are all standing wave, but you can see that they are oscillating at different speed. The one to the left is kind of slow, and the one to the right is kind of faster, right? So if you talk about the frequency, omega, right, the one in the left is lower omega compared to the one to the right. So you can have different standing wave with different frequency, right? So next, I'm gonna try to show you like what's the condition for this thing to happen. And it's gonna be a little bit more math, but not too bad, I hope. Okay, so everyone should be clear on this topic. I don't want that yet. All right, so standing wave on a string, but this gonna apply to any other cases also. But to use the most familiar picture that you all have, standing wave on a string. Essentially, the difference here is what we call the boundary condition, and it's gonna say like what actually happens to the string at the end and at the beginning. Okay, so we're gonna look at this what we call boundary condition, and we're gonna say that let's fix both ends of the string, kind of like a guitar string on a guitar, right? It's fixed on the guitar. One end of the string is not oscillating freely, otherwise you cannot keep the string on the guitar, right? So this is kind of like that. So both ends of the strings are fixed. What does it mean for the string to be fixed mathematically? Mathematically, it means you cannot have any displacement of the string at the endpoint. So if we set up the coordinate, the x variable to tell you the horizontal position, I can call this to be x equal to 0. I can call this one to be x equal to L. So you can say that L is related to the length of the whole string, right? And that's fixed, okay? The 2 points of the string which is fixed are x equal to 0 and x equal to L. So it means that if we have any wave inside, described by function y, which is as a function of x and t, okay? we are trying to find what is y. So fixing n means y at x equal to 0 at any time has to be 0. Remember what y is. Y is the displacement of the string. So fixing the string at x equal to 0 means it cannot have any displacement at that point. So that's the left end. The right end is x equal to L at any time must also be 0. That's how we translate this words or phrase into a mathematical condition or mathematical conditions, because we have two of them. This technically we call boundary conditions. And it's required for solving the wave equation, what we are trying to, or we're kind of trying to solve it, but not in a very dramatic way. We're just trying to find a solution that satisfies these two conditions, which is what we call the boundary conditions. Okay, so some of you might have studied, differential equations. You know that in order to find a solution, you need to know usually the initial condition, right? For example, what's the velocity at time equal to 0? What's the velocity at time equal to whatever, right? And that's gonna help fixing the solution. In this case, remember, because we have two free variable x and t, right? So this is kind of like the initial condition, but in the x variable. But I mean, it's the position, right? So it doesn't really make sense to call it like initial or final. So that's why we call it boundary. Okay, that's fine. Let's write down the solution for y that we had earlier. So remember, we are trying to find the standing wave on a string or in a string. Or I don't know what's the correct preposition here, because it's kind of both in and on. But anyway, we know from this page, when we did the math, we add the two waves together, incident and reflected wave. This is what we get in terms of the function. Okay, so let's try to write that down. So we have 2a sine kx cosine omega t. That's what happens when you add the two waves, which goes in the opposite direction together. Okay. Now what we're gonna do is we will try to find the condition for k such that these two conditions are fulfilled. We didn't talk about these two conditions in the previous page, so we didn't really care what k is. And remember, what is k? K is the wave number, is 2 pi over the wavelength. So the question that we are trying to answer here is like, what is the permitted wavelength of the wave that you can put in here in order to get a standing wave? So let's try to do the boundary condition. So let's use the first one. I call it this first condition. First condition is kind of trivial because the way we set up the function. So y of x equal to 0 at any time must be equal to 0. Do we have that? Yes, because 2a sine of kx when x equal to 0 is always going to give you 0. So it's automatically satisfied. We didn't have to do anything. Actually, it's kind of useless for us because it does not give us any new information. But at least we show that it satisfies the first condition. Now what about the second one? The second one is x equal to L times here, t equal to 0. And here we have to have 2a sine k times L, right? X is no longer 0 because it's the right end of the string. So x equal to L. And this has to be equal to 0. And it cannot be 0 at just a few times. Like this point in time is 0, but the other point in time is non-0. It cannot be like that. It has to be 0 for all time. And in order for that to be true, then this has to be 0. Okay? Cosine omega t can be anywhere between -1 and 1. It doesn't matter, right? As long as you have sine of KL equal to 0, then this condition is automatically fulfilled. Okay? So this gives us this condition that sine of KL must be equal to 0. And that just means you cannot just pick any wavelength, because the wavelength that you pick gonna tell you the value for k, and that value for k might not satisfy this condition here. Right? So what value of k that can satisfy this equation? Well, sine of what equal to 0? Sine of any multiple of 2 pi is equal to 0. So that means KL must be some integer. I'm going to use m here in order to be distinct from n that we used earlier a while ago. But m is an integer. And for this integer, we are not going to start from 0, because that's going to be, that's going to give you no wave at all. So we don't want that. So m going to start from 1 and 2, 3, 4, 5, whatever, like this. Okay? So don't pick 0, because there's going to be 0 everywhere. We don't want that. So KL is equal to m times 2 pi. This is going to give you sine of KL equal to 0. So what does it mean? It means that, not 2 pi, just pi, right? Because sine of 0 is 0, sine of 180 degrees is also 0. Okay, so it's not multiple of 2 pi, it's multiple of pi. Okay, multiple of 180 degrees equal to 0 here. All right, so that means k, which is 2 pi over lambda times L, must be equal to m, an integer, times pi. So pi cancel out. Lambda has to be 2L over m. This gives you the condition for allowed wavelength in order for standing wave to be in this string. Okay? If you pick lambda which does not satisfy this equation, the wave will not give you a standing wave. There will be some wave, but they're going to interfere like really randomly, and it's not going to look as nice as the standing wave that we have seen before. So only when you have lambda equal to this condition, then you're going to have a nice standing wave. Okay? When you pick lambda, that means you're going to force the frequency of the wave to be one particular value. Okay, so what do I mean by that? Remember this formula here, V equal to F times lambda. Okay, what is V? V is the wave speed, which is fixed by how you set up the system. In this case, it's given by the tension of the string divided by the mass of the string. Okay, so it's fixed. It's nothing to do with like what's the frequency of the wave you put in. It's the type of the string. You pick that, then that's it. Okay, so V is fixed. Now, because you have many value of lambda that's possible, from this equation, that means there's going to be some value of frequency that you can pick to have a standing wave in this string. Okay, so let's just look at the most basic case. Let's just pick the largest possible lambda. So the largest lambda is what? Well, lambda is 2L divided by m. The largest lambda means the smallest m, right? The smallest m is 1. And you can see now why 0 doesn't make sense, because you get infinity, right? So m equals to 1. So the largest lambda is when lambda equal to 2L. So the wavelength is twice the length of the wave. And what's the frequency? The frequency is V over lambda. So the frequency is going to be V divided by 2L. Okay. So remember the whole string is only a length of L long, but the wave that we have here is wavelength of 2L, right? So what we see in the animation is only half the wave because that's only half the lambda. Right. So in the animation, in the diagram, 2D static diagram, it looks like this. But it's actually only half of the wave, right? Because we only have half of the string. And that's when you go back to this animation here, that's the leftmost picture. That's here. Okay. So it's the wave going up and down like this. That's the lowest frequency that you can have for a standing wave. That means the wavelength is the longest possible, right? So in this case, the wavelength is twice L. So this is L, right? The length of the whole string. So wavelength is twice of that. Okay, so let's continue. How do I go back? Okay. All right. Now let's go to the next one. The next one is lambda a little bit shorter, frequency a little bit higher. So the next is when m equal to 2. So when m equal to 2, lambda is 2L over 2, which is just L. And the frequency is V over lambda, which is now L. Okay, so you can see that the wavelength increased, the frequency, the wavelength decreased because from 2L to L, from 2L shrinks down to L, and the frequency increased, right, because it's V over 2L, now it's just V over L. But in this case, the graph gonna look like this. Right. And this is when we have, for the next one in this picture, that's this one here. So you can see that the wavelength is shorter, the frequency is higher, so it's oscillate up and down faster than the one to the left. Okay, and you can keep on going. Next, you can say it's m equal to 3, so lambda is 2L over 3. So frequency now is 3V over 2L. So it's going to be something like this for the standing wave. Okay, and again in the animation, it's going to look like the third one that we had here. Okay, even faster in the frequency, and the lambda, the wavelength is shorter. And you can just keep on going, m equal to 4, m equal to 5. All right, so because the pattern that you can see here, right, this is the first one is the longest wavelength that you can fit in this string to get a standing wave. If the wavelength is any longer than this, then you're not going to have a nice standing wave in this string. So it's going to interfere like randomly. That also means this is the lowest frequency that you can have in order to get a standing wave, right? So because of that, sometimes we call this F subscript 0 because that's the lowest frequency. And that's what we call the fundamental frequency. Fundamental frequency. And fundamental frequency, it just means the frequency of the wave, the lowest frequency of the wave that you have to pick in order to have a standing wave in this system. Any lower than this, you're not going to have a standing wave. Okay, so we have this fundamental frequency. And the next frequency is f equal to v over L. So it's by no means an accident. There is actually just twice f0, 2 times. The next one is also no accident, is 3 times f0. And you can guess, if you work out the math, then you're going to have f equal to 4f0, 5s0, so on and so forth. Okay, and because of this, sometimes this will be called f2, this will be called f3, because it's 2 times the fundamental frequency. So it turns out that any frequency which is multiple of the fundamental frequency gonna have a nice standing wave in the system. Okay, so we are running out of time today. We're gonna continue next time. But this is sometimes called the harmonic frequency. Harmonic frequency. So F2 sometimes is called the second harmonic, which just another name of saying that it's the frequency which is twice the fundamental frequency. And next one you can guess is the third harmonic, fourth harmonic, fifth harmonic, so on and so forth. So the harmonic is the multiple of the fundamental frequency, right? So every harmonics are the frequency that you can have in terms of the standing wave. All right, so before I finish, let me go back to this for a moment and then run this again. 1, 2, right? So what we are seeing here, we have the fundamental frequency f0. And then we have the second harmonic, f2, which is equal to twice the fundamental frequency. And then we have the third harmonic, which is 3 times f0. And then we have the fourth harmonic, which is 4 times f0, like this. Okay. So all of these are valid standing wave. Okay. But they are standing wave of different harmonics. So they're going to have different frequency and different wavelength. All right. And so next time we're going to talk a little bit more about this and apply this to like the sound wave case, which is standing wave in an air column. So I will see you on Monday. And I think that's all I want to say for today. All right. So again, thanks for showing up, and see you on Monday. So take care and see you later.